Hi everyone, in this week's lesson number 4, we're going to talk about limiting and excess quantities. Now what the big idea here is the amount of product you produce is limited by the amount of reactants you have. So what have we assumed so far in all the calculations we have completed? Well, one of the biggest things that we have assumed was this. All reactants are fully used up. What that means is we are assuming, for example, when we reacted HCl plus NaOH, when it reacts, it gives you H2O plus NaCl. We're assuming that when we react these two, the HCl and the NaOH is fully used up. They're fully used. But this is not the case. It actually doesn't happen in real life. In real life, we end up having one of the reactants will always get used up first. Only one reactant is fully used up. So because of that, we end up having a case where we have something called limiting reagent. It's the one that gets fully used up. We call this a limiting reagent. Well, because that the rest of the reactants remain. And we call these excess reagent. Now, you have, so in this case this should be you, have 1 liter bag of flour. You also have 1 liter bag of sugar. Which one will be used up first if you're baking, for example, a cookie? In this case, obviously, your flour will be used up first. And because it will be used up first, this is your limiting reagent. Your sugar will remain. And because it will remain, this is your excess reagent. So this is how you use the word excess reagent and limiting reagent. I can show you this with a simulation from PhET. PhET is a great tool if you've never used PhET before. It is an amazing website built by the University of Colorado Boulder that allows you to run simulations of various things. This wants to show you limiting excess with different versions. So let's start off with a sandwich. Let's say, for example, in this sandwich, you're trying to make a grilled cheese sandwich. You need 2 pieces of bread and 1 piece of cheese. If you have, for example, 8 pieces of bread and only 1 piece of cheese, you're going to make one sandwich, but you're going to have a lot of bread remaining. In this case, your bread is your excess reagent. Your cheese is your limiting. As you keep on reacting or adding more cheese, you're going to start using up that bread. Eventually, you can run to a case where you have a perfect reaction where both of these are fully used up. You're going to need 8 pieces of bread for 4 pieces of cheese. But what happens if we add 1 more piece of cheese? Well, when we do that, now what is our limiting? Our limiting is now our bread. We're limited by how many grilled cheese sandwich you can make by the amount of bread. Because now you're going to have an excess amount of cheese, which is your leftover. And no matter how much cheese you add, you're always going to have that as excess. So this is an example of a real-world situation dealing with limiting and excess reagents. What if we're talking about molecules? What if you're talking about water? Where we have this reaction, 2 hydrogen molecules reacted with 1 oxygen molecules gives you 2 water molecules. You could have a ton of oxygen molecules, but if you just have 2 hydrogen molecules, you'll form 2 water, but you have excess amount of oxygen. And as you can see, you have leftover oxygen molecules. So this is what we call excess limiting. You're limited by the amount of hydrogen gas you have. You have excess amount of oxygen. So this is what we mean when we're discussing limiting and excess. Well, why do we have excess amount? Why can't we just have a set amount of reactants always? Well, one of the big things why, one of the reasons why is because the excess amount forces the limiting to be fully used up. Now, why? Why is that the case? Why do you want excess amount? Well, sometimes the limiting may spoil. And because it may spoil, you want to use it up. So if it could spoil, it could go bad, you want to be able to use it up, so you add a lot more excess to get rid of it. Another reason, it's harmful. Because of that, you want to react to use up. So that's another reason why that is the case. But one of the most common reasons why you have excess amount, it's natural. Example is for a combustion reaction, you always have oxygen gas as a excess, because oxygen gas airs all around us. So that's why we always have, in this case, excess amount. So what are some terms we need to know? What are some terms we need to know for this lesson? Well, some terms we need to know is, number one, we need to know of obviously limiting reagent, which we talked about earlier. This is the reactant that gets used up. While excess reagent, this is the reactant that remains at the end of the reaction. Okay. But there's two more words we're going to learn, and they're not going to come into play that much this week. But we're going to talk about it in terms of their significance for this lesson. The third word we're going to learn is theoretical yield. What this is the yield expected. That means how much product you expect to make from calculation. So from your calculation, what do you expect to make from your limiting reagent? That's your theoretical yield. Wow, from actual experiment, you have your actual yield. This is the yield, how much product you will get from experiment. So when you actually do the experiment, what is your actual yield? So these are four terms we're going to use quite often in the next two lessons. So let's go over strategies on how to solve for limiting excess reagent. So what do you want to do? Well, step one. From your mass, for example, if you have mass, volume, or particles, convert this to moles for all reactants. So that's the first step. You want to convert whatever mass, volume, particles you have, convert to the moles for all reactants. Number two, convert all moles to one product moles by crossing the mole bridge. So you want to convert all the moles that you just converted in step one to one product moles. Now, why do you want to convert to one product moles? You could find which one will produce the smaller amount of product. So in this case, number three, the one that produces the least amount of product is your limiting. That means the rest are your excess because they will be remaining. Well, these are the 3 steps to find what is limiting excess. How do you find how much of your excess will remain after reaction? How would you find what will be left over after your reaction is completed? Well, we can convert this because what we're going to do is we're going to take step 1, convert your limiting reagents moles to the moles of each excess reagent. So what you're going to do is you're going to take your limiting reagents moles, whatever that is, and you're going to convert it to the moles of each excess reagent you have. What's step 2? Step 2 is subtract starting amount of each excess reagent moles by moles of each excess reagent used up. And where does this value come from? The moles of each excess reagent used up? Well, that will be found in step 1. So when you convert your limiting reagent moles to the moles of each excess reagent, you're finding what is used up. So the last step is now, step 3 is to convert step 2 remaining mole of excess to the mass of each substance. So that's how you find how much of each reagent that is excess is going to remain. Now, the biggest thing is we refer to moles, not mass, when we're looking for limiting reagent. So we're not looking at which one has the least amount of mass, that's the limiting. We're looking at which one produces the least amount of moles of product. So just because something has a smaller mass doesn't mean it's limiting. And a limiting reagent question will always show enough information to solve for which is limiting. So let's practice. Let's practice these steps to solve. Let's look at example number 1. So in this reaction, you have aluminum reacting with iodine to form aluminum iodide. Now in this case, this reaction is not balanced because you're going to need to actually put a 2 in front of this aluminum iodide to fully balance it. So what you want to do is you want to determine the limiting reagent and the theoretical yield of the product if 1.20 moles aluminum and 2.4 moles of iodine reacted. So what we're going to do is, well, these units are already in moles. So we want to take 1.20 moles of aluminum and cross the mole bridge to find moles of aluminum iodide. That's one of the products. Sometimes you're going to have more than one product. You have to choose which product to convert to. So let's convert to aluminum iodide. So in this case, it's a 2:2 ratio. So you have 2 moles of aluminum iodide over 2 moles of aluminum. In this case, you're going to get 1.2 moles of aluminum iodide created. Okay, let's take this for iodine. Iodine is 2.4 moles of iodine. And you're going to have to cross the mole bridge again, 2 moles of aluminum iodide over 3 moles this time of iodine. So if I forgot to cancel units to show you, so this time you're going to get, if you look at your calculations, 2.4 times 2 divided by 3, you're going to get 1.6 moles. 1.60 moles of aluminum iodide form. So looking at this then, which one produced the least amount of moles of your products? Is it the aluminum or is it the iodine? From here you can see that your aluminum will produce the smaller amount. And because it's smaller, your aluminum is your limiting. Your iodine is your excess. So because of that, your aluminum being your limiting, you can now find how much aluminum iodide you have formed, because you will not create 1.6 moles of aluminum iodide. You just won't. The moment this reaction creates 1.20 moles of aluminum iodide, the aluminum would have been fully used up. You would have used up fully the aluminum to create this much aluminum iodide. So you're going to have some iodine, I2, remaining. Well, how much aluminum iodide would you form? Well, to solve that, you take your moles to find your theoretical yield and you multiply it by the atomic mass of aluminum iodide. So in this case, it's 27 for aluminum plus 3 times 126.9. And you're going to get 407.7. So you take this the moles, and you multiply it by 407.7 grams per 1 mole of aluminum iodide. And that should give you your theoretical yield of aluminum iodide. In this case, it's going to be 489 grams. And this is what you call your theoretical yield. It's not your actual yield, because actually you may be forming something a lot less. You could never form more than your theoretical. And we're going to go into that as our next lesson. Let's try our next question. What if this time you're given not moles of each of them, you're given grams of each of them? Well, in this case, if you're given mass, your first step is to convert these masses into moles. So you have 1.20 grams aluminum. You want to now multiply and solve for moles of aluminum. So what is the molar mass of aluminum? It's 27.0 grams. Okay. Once you have moles of aluminum, your job now is to cross the mole bridge to get to moles of one product. So it's 2 moles aluminum iodine over 2 moles of aluminum. So you're going to now have fully solved for your moles of aluminum iodide, your product that you want to convert to, because you always want to convert to the moles of a product. So if I punch this on my calculator, 1.2 divided by 27 times by 2 divided by 2, I will get 0.044 repeating moles of aluminum iodide. If I do this now with our iodine, 2.40 grams times 1 mole of iodine over. So in this case, you have I2. The chemical here you're dealing with is I2, so that should be an I2. So what is 2 iodine's molar mass? Well, if 1 iodine's molar mass is 126.9, I can multiply this by 2 to get 253.8. So be careful when you're doing this. It's I2, because iodine is a polyatomic ion. So that should have been I2 right here as well. So then again, you multiply to solve for your mole ratio to get to aluminum iodide, which is 3 moles, 2 moles, 3 moles this time. Y2. You cross out the values you already canceled out. And this time, you're going to solve for your moles of aluminum iodide if you had 2.40 grams of iodine. So 2.4 divided by 253.8 times by 2 divided by 3. And you're going to get 0.0063. 0.0063, in this case 630 moles of aluminum iodide. So let's look at this time. Which one produces the least amount of moles of your product? Is it the aluminum or is it the iodine? As you can see here, this time, this is your smaller amount. It's a smaller value. Thus, this is now your limiting. That means this is now your excess. So your aluminum this time is your excess. Your iodine is your limiting. What that means is your iodine, all 2.4 grams of it will get fully used up before your aluminum gets used up. And once you produce 0.00630 moles of aluminum iodine, this reaction will stop because all of your iodine would have been used up. So let's calculate our theoretical yield then. In this case, our theoretical yield will be based on our limiting. So again, I'm going to multiply this moles by 407.7 grams over 1 mole of aluminum iodide. And now you're going to see that because that you could find that you're going to theoretically solve and get, according to this, you're going to get 2.57 grams of aluminum iodine form. And this is again your theoretical yield. Alright, so how many grams of aluminum are left over in part B? Well, that means because our aluminum is our excess, we're trying to find how many grams of our aluminum will be left over. So our first step is we're trying to find how many grams of aluminum is used up. Well, how do we find that? What we want to do is we want to take our limiting, which in this case is iodine, and convert it to how many. In this case, we actually convert directly, even though our notes does say you want to convert your limiting reagent moles to the moles of each excess reagent used up. Subtract the moles. Another shortcut you can do is you can actually convert this limiting reagent's mass to the mass of aluminum used up. Because if you take 2.4 grams of iodine and convert that all the way to aluminum, you're actually going to find how much aluminum is used up. So you're doing an additional step. You're basically taking all these steps that you have here and combining them into one single step. So let's try that. So you're going to have 2.40 grams of, in this case, iodine, times by, again, 1 mole of iodine, because you want to get to moles always, and its molar mass. So your grams will cancel out. But this time, instead of converting to moles of aluminum iodide, you just want to convert to moles of aluminum, which is still 2, based on the balance coefficient. 2 moles of aluminum over 3 moles of iodine. So that will cancel out. Our last step is now to multiply these moles of aluminum to the mass of aluminum. So if we do that, we're going to multiply by its molar mass, which is 27 grams over 1 mole of aluminum. So once we cancel this out, we're going to get the mass of aluminum that gets used up if we just react 2.4 grams of iodine. So if I punch this all into my calculator, times by 2, divided by 3, times by 27. We're going to find that 0.1700 grams of aluminum used. This is how much aluminum we used up. Well, how much aluminum did we start with? We started with 1.20 grams started. If we want to find how much left over, we subtract it by how much was used up, and we will find that we have 1.03 grams remain. That's how much of aluminum will remain. So this is aluminum. So after all 0.170 grams of aluminum is used, we're going to remain only with 1.03 grams of aluminum. So that's how we find how much aluminum is remaining, because we find what we started with and we subtract it by what we used. Let's practice that with our next equation. Example number 2. If 15.00 grams of aluminum sulfide, which is right here, and 10 grams of water, which is right there, react until the limiting reagent is used up, it will form one of these. Now, which is the limiting reagent? So you want to convert both of these grams to moles, and then to moles of one product. Which product should we convert to? The aluminum hydroxide or the hydrosulfuric acid? Well, sometimes you might want to convert to whatever the next question is asking. Because you look at the next question, you see what is the mass of hydrosulfuric acid that can be formed. So it'll make more sense to convert it to hydrosulfuric acid. So in this case, let's convert both of these to moles of hydrosulfuric acid. So we have 15.00 grams of aluminum sulfide, and we want to solve for it to get to moles of hydrosulfuric acid. Well, what is the molar mass of aluminum sulfide? Well, there's 2 aluminums plus 3 sulfurs, which is 32.1. We should get a full molar mass of 150.3. 150.3 grams. Now our next step now is to convert to moles of hydrosulfuric acid, which is 3 moles of hydrosulfuric acid over 1 mole of aluminum sulfide. So what we have here is our grams cancel out, our moles cancel out, and we're left with just moles of hydrosulfuric acid. We're going to do the same thing with water. So we have 10.00 grams of water times by 1 mole over the molar mass of water is 18.0 grams times by this time it's 3 moles of hydrosulfuric acid over 6 moles of water. So again, you will see the grams cancel out, the moles cancel out, and you're left with hydrosulfuric acid. So, let's go solve for how many moles of each you'll form. So 15 divided by 150.3 times by 3, you're going to get 0.2994. So 0.2994 moles of H2S formed. Let's do the same this time with the next one. For water, 10 grams divided by 18 times by 3 divided by 6. And we're going to get 0.2778 moles of H2S formed. So looking at this, which one is your limiting? Well, which one produced a smaller amount of moles? You could see that it's your water. This one is smaller. And because of that, your water is your limiting. While your aluminum sulfide is your excess because you produce more of your product. So that means we take this limiting mole and solve for question number 2. So we take 0.2777 repeating, because I don't want to round to the very end, and multiply that by the molar mass of H2S, which we find is 1 plus 32, it's 2 plus 32.1, which is 34.1 grams per mole. So you take this and multiply it by 34.1, and you're going to get 9.472 grams of H2S formed. So as you see, you could see that we have our mass of H2S formed. The moment this much H2S is formed, this reaction should stop. Okay. Then how much excess reagent remains after the reaction is completed? aka, how much aluminum sulfide will remain at the end? Well, if we just calculate that the water is limiting, we could take our mass of water and convert it to how much aluminum sulfide was used up. So what I'm going to do is I'm going to take my 10 grams of water. So 10 grams of water. And I'm going to multiply and try to get to what is the mass of aluminum sulfide that is going to be created. So the molar mass of water is 18. So that will cancel my grams to get to moles of water. But this time I'm going to cross the mole bridge not to our product, but to my aluminum sulfide, which in this case is 1 mole. 1 mole, so that should be a 1 mole. 1 mole of aluminum sulfide over 6 moles of water. Okay. And last but not least, I'm going to solve for the mass of aluminum sulfide, which is 150.3. So I'll multiply this by 150.3 grams over 1 mole of aluminum sulfide. And that will allow me to find what is the mass of aluminum sulfide that I used up. So if I punch this on my calculator, 10 divided by 18 divided by 6 times 150.3. I'm going to see that I used up 13.916 repeating. So 13.916 repeating grams used. So that's how much aluminum sulfide I used. Well, how much aluminum sulfide did I start with? I started with 15 grams. So what I want to do, the last step, is to now subtract 15.00 grams, subtracted by 13.916 repeating. 916 repeating grams. I'm going to get what value? So 15 subtracted by 13.916 repeating. I'm going to get 1.083. 1.083 grams remain of aluminum sulfide. So that's what's going to remain at the end of this reaction. So as always, if you want to pause this video at any time, make sure you do so you can practice these questions, because we're going to go over example number 3, which is our last question of today. Alright, so example 3 now has multiple things getting reacted. You have 60.7 grams of FeCl2, you have 15.2 grams of KNO3, you have 42.6 grams of hydrochloric acid. What is your limiting? Well, you always want to figure out which product you want to convert to. But if you look at the next question, there is no product to convert to. So you could choose. For just the sake of this reaction, I'm going to try converting to. Let's do it and convert to the first element here, which is FeCl3. So let's start with the first one, FeCl2. Okay. Now FeCl2, I have 60.7 grams of it. Now my first step is to convert it to the moles of FeCl2. Well, what is the molar mass of FeCl2? Well, FeCl2 has a molar mass of 55.8 plus 35.5 times by 2. You're going to get a molar mass of 126.8. So you're going to have a molar mass of 126.8 grams. Okay, so as you see, your grams will cancel out. My next step now is to now cross the mole bridge to get from FeCl2 to FeCl3. So in this case, it's 3 moles of FeCl3 over 2 moles of FeCl2. So your moles of FeCl2 will cancel out. So now you get to moles of FeCl3, you're good. You now could find if it's limiting or not. But let's try the next few examples, the next few things first before we calculate. So KNO3. You have 15.2 grams of KNO3. You want to multiply by the molar mass, but you want to divide it in a sense by 1 mole of KNO3 over whatever the molar mass of KNO3 is. So in this case, KNO3. K is 39.1 plus N, which is 14, plus 3 oxygens, which is 48. You're going to get 101.1. 101.1 grams of KNO3. So your grams will cancel again, and your next step is to cross the mole bridge, which in this case is 3 moles of FeCl3 over 1 mole of KNO3. And again, your moles of KNO3 will cancel out. Okay, your last step is to now convert the last chemical, which is HCl. So your HCl is, in this case, you have 42.6 grams times 1 mole of HCl over, what is the molar mass of HCl? It's 36.5 grams. Times by the mole ratio, this time it's 3 moles of FeCl3 over 4 moles of HCl. Alright, so now we can now find what is our limiting. So let's solve each of these to solve for limiting. So we have 60.7 divided by 126.8 times 3 divided by 2. Our first one is going to be 0.718. So 0.718 moles of FeCl3 will be formed. If I could find this thing, there it is. So 0.718 moles formed. Okay, our next one. 15.2 divided by 101.1 times by 3, I get 0.451. 0.451 moles. So judging by these two, KNO3 is less than FeCl2, so it's going to be more limiting right now. But let's try HCl. HCl is 42.6 divided by 36.5 times by 3 divided by 4. And we're going to get 0.875. 0.875 moles. So judging by this, which one is limiting? Which one produces the least theoretical yield? Well, KNO3. KNO3 here is your limiting because it's the one that produces the least amount of product. The other two are your excess. Yes, you can have multiple excess because anything that gets remaining is your excess. So your 15.2 grams, the moment 15.2 grams of KNO3 is used up, this reaction will stop because you'll form this much product. So that is how you find limiting. How would you find how many grams of excess will be present after reaction? Well, it's the same as previously. You're going to take your grams of what you have limiting and convert to mass of what is used up. So you started with 15.2 grams of KNO3. You now got to convert to the mass of FeCl2 and HCl. So you have 15.2 grams divided by 101.1 grams of KNO3. But this time you're going to cross the mole bridge to get to FeCl2, which is 3 moles of FeCl2 over 1 mole of KNO3. So your grams cancel out, your moles cancel out. Your last step is now to convert to the mass of FeCl2, which we found earlier was 126.8. So it's 126.8 grams over 1 mole of FeCl2. Okay, what is your mass that's going to form? Who knows? We'll figure that out in a bit. Your next one is to take the same thing, 15.2 grams, times by 1 mole of KNO3, but this time you convert it to HCl. So you convert this to the moles of HCl, which is in this case is 4 moles of HCl, over again 1 mole of KNO3, times this time what's the molar mass of HCl? It's 36.5 grams over 1 mole of HCl. So you're going to now this time solve for how much HCl is used up in this reaction. Okay, so let's plug these into our calculator now. And we could see that with our calculations here, we have 15.2 divided by 101.1 times 3 times 126.8. And we could see that K03, we used up 57.19. So 57.19 grams used initially. Okay. We started with 60.7. So how much remains? Well, 60.7 grams take away 57.19 grams. We will see that we should have, in this case, so 60.7 take away 57.19. We should get 3.51 grams remain because it's 3 sig figs. This is for FeCl2. Let's do this with HCl. So with HCl, how much is used up? 15.2 divided by 101.1 times by 4 times by 36.5. And we see that we used up 21.95 grams used. Well, how much HCl did we start with? We started with 42.6 grams. We used up 21.95 grams. How much remains? Well, 42.6 grams take away 21.95 grams. We're left with 20.6 grams remain of HCl. So this is how you do this with multiple questions, multiple of these. Now, as always, make sure you complete your homework, which is page 133, numbers 26 to 32. Stay safe and healthy, and I'll see you soon.